Welcome you all. I am Dr. Jahan, Associate Professor, Electronics and Communication Department from Rohini College of Engineering and Technology, Kanyakumari. So this video I have discussed about ADA wireless sensor networks. IEEE 802.15.4 MAC protocol. The Institute of Electrical and Electronics Engineers (IEEE) released the 802.15.4 MAC standard for wireless personal area networks (WPAN), equipped with a duty cycle mechanism where the size of active and inactive parts can be adjustable during the PAN formation. Network architecture and types roles of nodes. The IEEE 802.15.4 MAC combines both the schedule-based and the contention-based protocols and supports two network topologies, star and peer-to-peer, as shown in figure. Application of IEEE 802.15.4 wireless sensor networks, home automations, home networking, connecting devices to a PC, home security, etc. There are two special types of peer-to-peer topology. The first type is known as a cluster tree network, which has been used extensively in ZigBee. The other type is known as a mesh network, which has been used extensively in IEEE 802.15 wireless PAN task groups 5 TG5. The standard defines two types of nodes, namely the full function device (FFD) and the reduced function device (RFD). The FFD mode can operate with three different roles as a PAN coordinators and a device, while RFD can operate only as a device. The devices must be associated with a coordinator in all network conditions. The multiple coordinators can either operate in a peer-to-peer topologies or star topology with a coordinator becoming the PAN coordinator. The star topology is more suitable for delay critical applications and small network coverage, while the peer-to-peer topology is more applicable for large networks with multi-core requirements at the cost of higher network latency. Furthermore, the standard defines two nodes on how data exchanges should be done, namely the beacon mode and the non-beacon mode. The beacon mode provides networks with the synchronization measures, while the non-beacon mode provides the asynchronous features to network. Superframe structures. The beacon mode IEEE 802.15.4 MAC defines a superframe structures to organize the channel access and data exchanges. The superframe structure is shown in below figure with two main periods, the active period and inactive periods. The active period is divided into 16 time slots. Typically, the beacon frame is transmitted in the first time slot and it is followed by two other parts, condension access period CAP and the condension free period CAB, which utilize the remaining time slots. The CFB condenser free period part is also known as guaranteed time slot GTS and can utilize up to 7 time slots. The length of the active and inactive periods as well as the length of the single time slots are configurable and traffic dependent. Data transfer can occur either in CAP or GTS. In CAP, data communication is achieved by using slotted CSMA CA, while in GTS, nodes are allocated fixed time slots for data communication. The strategies to achieve energy efficient operations in IEEE 2.15.4 MAC is by putting the nodes to sleep during the inactive periods and when there is neither data to be transmitted nor any data to be fetched from the coordinator. However, the burden of energy cost is put on the coordinator where the coordinator has to be active during the entire active periods. GTS management. The coordinator allocates GTS to devices only when the latter send appropriate request packets during the cap. One flag in the request indicates whether the requested time slot is a transmit slot or receive slot. In a transmit slot, the device transmits packets to the coordinator, and in a receive slot, the data flows in the reverse direction. Another field in the request specifies the desired number of contiguous time slots in the GTS phase. The coordinator answers the request packet in two steps. An immediate acknowledgement packet confirms that the coordinator has received the request packet properly but contains no information about success or failure of the request. After receiving the acknowledgement packet, the device is required to track the coordinator's beacons for some specified time called a GTS persistence time. When the coordinator has sufficient resources to allocate GTS to the node, it inserts an appropriate GTS descriptor into one of the next beacon frames. The GTS descriptor specifies the sort address of the requesting node and the number and the position of the time slots within the GTS spaces of the superframe. A device can use its allocated slots each time they are announced by the coordinator in the GTS descriptor. If the coordinator has insufficient resources, it generates a GTS descriptor for invalid time slot 0, indicating the available resources in the description's length field. Upon receiving such a descriptor, the device may consider recognition. If the device receives to GTS descriptor within a GTS description persistent time after sending the request, it conducts all the allocation request has failed. A GTS is allocated to a device on a regular basis until it is explicitly deallocated. The deallocation can be requested by the device by means of a special control frame. After sending this frame, the device shall not use the allocated slots any further. The coordinator can also trigger deallocation based on certain criteria. Specifically, the coordinator monitors the usage of this time slot. If the slot is not used at least once within a certain number of superframes, the slot is deallocated. The coordinator signals deallocation to the device by generating a GTS descriptor with the start slot 0 data transfer. Assume that the device wants to transmit a data packet to the coordinator. If the device has an allocated transmit GTS, it wakes up just before the time slots and send it back immediately without running any carrier sense or other collision avoiding operation. However, the device can do so only when the full transaction consisting of the data packet and an immediate acknowledgement sent by the coordinator, as well as appropriate interference spaces fit into the allocated time slot. If this is not the case, or when the device does not have any allocated slots, it sends its data packet during the cap using a slotted CSMA protocol. The coordinator sends an intermediate since the coordinator sends immediate acknowledgement for the data packets. Now assume the coordinator wants to send the data packet to the device. If the device gets allocated a received GTS and when the packet acknowledgement IFS cycle fits into this, the coordinator simply transmits the packet in the allocated time slot without further coordinations. The device has to acknowledge the data packet. The handshake between device and coordinator is sketched in figure 3.11. The coordinator announces buffer packet to device including the device address into the bending address field of the beacon frame. When the device finds an address in the bending address field, it sends a special data request packet during the CAP, slotted CSMA CA protocol. When desk have to send a data management control package during the CAP, they use a slotted CSMA protocol. The protocol contains no provisions against hidden terminal situation. For example, there is no RTS CTS handshake to reduce the probability of collisions. The protocol uses random delays. It is thus the CSMA CA protocol, CSMA with collision. The time slots making up the cap are subdivided into smaller time slots called pack-off periods. One pack-off period has length corresponding to 20 channel symbol time, and the slots considered by the slotted CSMA CA protocol are just these